Welcome back to Computer Science 163 at the University of Wisconsin-Eau Claire. This is mini lecture number 10 with Jess Riesma. We're joined by our co-host today, Galileo, my cat, and Kepler, his sister, is right next to us. So yeah, this will be fun. So today we're going to be talking about the binary search algorithm. This is described in your textbook, chapter 12.6.2. Now, just like the last one, Chapter 12 is not part of the actual textbook. It's like an e-chapter. So you can go to the publisher's website to access that, or for my students, who are probably the only ones watching this video, you all have access to the textbook through the campus license, and I've posted that chapter on online for you as well on Canvas. Some self-check questions. I'm going to go in backwards order here. First, be familiar with the functions in passing arrays by reference, and also be sure that you're familiar with simple algorithms from mini lecture number 8. Definitely be sure you're comfortable with the searching algorithm from mini lecture number 9. So what is the linear search algorithm? What is its best case run scenario? What is its worst case scenario? And what's its average case scenario? And then also, what is big O notation? And how do we use that to compare different algorithms? We'll learn a little bit more about that today, so don't worry too much. Binary search, what does that mean? It means that we're going to split the problem in half each time to reduce the total amount of guesses or computations or comparisons that we need to make. So with the linear search, we had to go in order from the first element in the array all the way to the last element of the array, or maybe we'd get lucky and we'd find it sooner. In the divide and conquer approach, we're going to basically reduce the amount of comparisons we need to make, and we're going to get a lot better performance. Let's go back to that game that we played last time. Remember when you were a kid and you were thinking of your friend was thinking of a number 1 through 100, and you tried to guess what it would be. Pop quiz. What was the approach for the linear search algorithm? What would the linear search algorithm do here? I'll let you pause it, and then I will come back and tell you. So pause, answer in 3, 2, 1. The linear search algorithm would say that you have to guess all of these numbers all in a row. So you could start at the beginning, guess 1, 2, 3, 4, 5. Or you could actually do it in reverse too. I mean, why not? You could do 100, 99, 98, 97, and that would be an example of the linear search algorithm. So the strategies for solving this puzzle and trying to guess quickly were what we discussed last time, either random guessing, which is really not very satisfactory and it takes a lot of guesses usually, and you better hope that you don't forget and guess the same number twice. You could also do a brute force approach. This is the linear search algorithm approach, and you basically guess every number all in a row. This also takes a lot of time. You could try to get lucky, and if you know that your friend has a favorite number, you could try guessing their favorite number or numbers. Or you could try dividing and conquering. If you can somehow split the possibilities in half each time, you would greatly reduce the amount of guesses that you'd have to do, if you can figure out a clever way to do this. And this is what the binary search algorithm is. And usually, it's the most efficient approach for this problem without fancier solutions. Let's visualize what that looks like. Here's that number line with numbers 1 through 100, and the green region represents the space where all the actual number could be somewhere in all of that green region. Now I know, as your friend, I know that 36 is what that is, so that's the actual guess. We're going to rule out regions progressively, and we're going to see what that looks like. So for guess number 1, you guess right in the middle because you want to divide this all the possibilities in half. You guess the one right in the middle, and you guess 50. So that's going to cut it into these two regions denoted by these blue lines, like that. And I'm going to tell you if it's higher than or less than that. If it's lower than, we'll eliminate all of the upper region, and if it's greater than, we'll eliminate all of the lower region. And I tell you that my number is less than 50. So that means that you've eliminated all of the numbers in one single guess. You've eliminated half of the numbers. So it's not 50. It's not any of the numbers between 50 and 100. Now the only possible values are between 1 and 49. That's really powerful compared to what the linear search algorithm was. So here's your guess number 2. You've got this region, all the numbers between 1 and 49, and you want to divide that space in half. So you guess 25, roughly in the middle. That's going to divide the space up into two regions, and one of those will eliminate, and one of them we will keep, possibly. So you guess 25, and I tell you, oh, it's actually greater than 25. My secret number is greater than 25, and so then you've eliminated now all the numbers 50 through 100, and now also you've eliminated 1 through 25, because you know it's not 25. It's not just not less than 25, but you've also eliminated that middle number, 25. So now you know my value must be between 26 and 49. That's 75% of the values eliminated in just 2 guesses. Powerful. Next up, you guess on the third one, you want to guess in the middle of this green region to divide this region up in 2, so you guess 38. 38 is roughly in the middle, and so I tell you my number is less than 38, because remember it's 36. So by telling you it's less than 38, you know it's not 38 or greater, and you've eliminated that region there. Now we're only left in this green region here as the total possibility space, between 26 and 37. So now in this region, you again apply the binary search algorithm, and you say, I want to choose the middle value right here, 31, and I tell you whether it's greater or less than. I tell you it's greater than 31. That means that you can eliminate all of those other spaces that were less than 31, and you can eliminate 31. So now it could be between 32 and 37. So guess number 5, you want to split that region up as evenly as possible, and now PowerPoint can't even draw arrows that small easily. So you guess 35, and I tell you my number is greater than 35. Now it's either 36 or 37. Now, okay, so do it one more time. Guess number 6. You guess it's rounding up, you guess 37, say, and I say it's less than 37. And then you're like, oh, hey, there's only one remaining. It must be 36. So that means on your 7th guess, you'll guess the value 36, and you've won. That's an amazing improvement versus the linear search algorithm, because in the linear search algorithm, it would have taken me 36 guesses, or it would have taken you 36 guesses to guess my number of 36. But here, it took you just 7 times. Pretty powerful. This binary search algorithm might therefore feel, magical almost. And in some ways it is. It's a really clever way to, it's a really efficient and optimal way even to figure out what that number might be. So it's perfect for this game. But it's not perfect for all problems. It's not a one-size-fits-all. So I want you to pause here and think, what are some of the advantages and the disadvantages of using the binary search algorithm? What are some of its requirements, and what does it do well, what does it not do well? So pause, and I'll give you the answers in just a sec. 3, 2, 1. One of the disadvantages is in the form of a requirement. In order to use the binary search algorithm, you have to have an array that is sorted. If you don't have an array that's sorted, you can't say, you can't choose the middle element in your array and then be assured that half of the elements below that with a smaller index are going to be less than that, and you can't assume that all of the elements that are above that middle point are greater than that middle point. So you need to have a sorted array where all the elements are sorted in ascending order in order to use this. And there are backwards versions where you can do it in descending order, but ignoring that. But that's basically how the binary search algorithm works. The advantages, of course, is that it's really fast. And the principle is this: you check an element, you check the middle element, and you either get a match, or you remove half the possibilities, or you run out of elements to search. So you check the middle one, and you either eliminate all of the ones lower and only have to check the higher ones, or you eliminate the higher ones and only have to check the lower ones, or you get it right, or there's nothing else to check because you've checked this one and this was your last option. And that means that you've run out of elements. It's not in this array. We're going to go back to that motivating example from mini lecture number 9, where we had 2 parallel arrays of size n, one with area codes and one with the strings of locations that correspond to those area codes. What we want to do is we want to say, okay, given an area code that we're trying to look for, see if that area code is in that array. If so, use that index where that area code is found, to find the location, the corresponding location in the second array. So if I say area code 616, then you tell me, oh, that's in Grand Rapids, Michigan. That's index number 3, or something like that. We've already done the linear search algorithm. Now we're going to see how that works with the binary search algorithm. Here's the picture again. So on the left, we have the array of area codes, integers, and then on the right, we have the array of strings containing the locations. And they're color-coded here, and they correspond to each other. The pseudocode for the binary search algorithm is the following. If the key equals the middle item, what do we mean? The key is the thing that we're using to find. So if I say I want to know what location area code 616 corresponds to, then 616 is the key. That's my search term, if you will. The middle item is the thing that's in the middle of the array. So first check the middle of the array, and if the key equals that middle item, hey, we found a match. Great, we know where that is, and we're good. If that's not true, else if, then we say, is the key less than the middle item? So in that matching game, for instance, is my number less than or greater than the number that you guessed? If the key is less than the middle item, then search the first half of the list with the lower values, the values that are lower than the middle item. And if that's not true, then the key must be higher or greater than the middle item, because it's not equal to and it's not less than. So the key must be higher than the middle item that we just checked. If that's true, then search all the things in this the second half of the list, the things that have higher values than the middle item. So repeat this entire process using each new half. So do this once for the middle of a list, and then if you're searching the upper half of that list, then look for the middle of the upper half of the list. And then see if you have to go up or down. And keep splitting the list in two, roughly, each time, and that's it. That's the binary search algorithm. So here's the binary search function actually implemented. So here, what we're doing is instead of returning the index directly as the return value of this function, we're going to return it as a reference parameter. So this function is going to have a void return value. It's not going to have a return value. The first argument is int num area codes, which is the number of area codes in the array. And we don't have to really focus on just area codes. It's the size of the array. It's array size. The next parameter is const int area codes, which is an array of integers. That's the array of possible values that we're looking for. And again, that has to be sorted. Then int key, that's the value that we're looking for. So that's the thing, that's our search term, if you will. Bool found, we're passing that by reference. That's going to be an output reference parameter. So we don't care what its value is coming in, but we're going to store a Boolean, either true or false, to tell us whether we found a value in the array. So is key, is that value contained in area codes? And then we're also going to return an integer called found at, which is the index that we found that in. So if found is true, if we did find that value, then that index will be stored in found at. And if not, then we don't care whatever the value is in found at. We won't set that. Okay, so that's the function prototype. That's the signature. The body of this function is first going to initialize a couple values. First, last, and middle. First is the first index in the region that we're searching. Last is the last index in the region we're searching. And mid is the middle one. That's our guess, if you will. We're going to set false or found equal to false. We haven't found it yet. We're going to set first equal to 0 and the last equal to the last element in the array. Then here's the loop for that binary search function. While first is less than or equal to last and not found. So the first part here, the first red thing, first is less than or equal to last. That's saying basically, as long as first is less than or equal to last, then we're saying that they're different or equal, and that means that there's still work to do. We haven't found the key yet. We're still trying to narrow it down. The found variable, remember, right now it's false because we haven't found it yet, and so exclamation point times or in front of a Boolean means not that. So not false meaning true. So we're going to keep looping until we find it, as long as finding it equals false, if you will. So inside of this loop, we're first going to figure out what the midpoint is, where the middle of this domain that we're looking at is. So take the integer, or the value of first plus last divided by 2, so that's the midpoint. Remember, integer division, so that's going to give us an integer result, ignoring the remainder. And then we're going to see if that value, or what our key is compared to that value. So first we're going to check and see, is the key, our guess, our search term, less than the area code in the middle? And then if so, then we're going to set the last thing up to, the last index equal to middle minus 1. So if we have 100 items, the middle will be 50, and then so the first will be 0, the last will be 99. But if the key is less than index, whatever is in index 50, then the last will equal middle minus 1. So now we're only looking for the elements between 1 and 49. That's on the one hand. On the other hand, if the key is larger than the middle value, then we're going to restrict the area to only the upper half. So it was between 0 and 99. Now we're going to set first equal to mid plus 1, so 51. So now we're only looking between 51, we're first, up to last 99, so 51 to 99. That's if the key is greater than the middle. If those aren't true, if it's not less than the middle and it's not greater than the middle value, then the key must equal the middle value. So in that case, else found equals true. We found a match, yay, and then that will stop the loop. We're also going to set the value found at equal to the middle index. Cool. And we're going to test this in almost the same way as we did for the linear search algorithm. So here's the main function. I've omitted the pound includes at the top in the using namespace standard. To compile, you'd have to include that, of course. So here are an array of integers, that's the area codes, and then an array of the corresponding locations, each has a string. So like for instance, area code 715, Eau Claire, Wisconsin, yay. And then we're going to ask the user to input the search, what area code are you looking for? And so they input something like maybe 802. Then what we're going to do is we're going to call the binary search algorithm, the function that we just wrote on the previous slide, and we're going to try to find where that is. What index is area code 802 located in? We're going to give it a bool called success, and if that comes out true as an output from the binary search function, then we know that we found it in the array, and if success equals false after calling that function, then we know that it didn't exist in that array. An index is going to be the index where that was found if success equals true. If it wasn't found, if success equals false, then we don't care what the value of index is. It doesn't mean anything. So we're going to pass it into the binary search function with the array size, 6, area code's the array, requested area code, what's the key. We're going to pass it success and index as well. We don't care about the values for that because, again, those are output reference parameters, not input reference parameters. So once we do that, we'll either get success and the index, or we'll just get success equals false, and we don't care what the index value is. So if success equals true, then output what the area code was and where it's associated with. We know that it was at index, so locations bracket index will be the string corresponding to that index, or corresponding to that area code. If success equals false, in other words, else, if success wasn't true, then just tell the user, oh, it couldn't be found, and exit. So that's the test for this routine. I think you can already start to see what some of the advantages are of a binary search over the linear search. If you're not sure, take a quick second to think through them. Make a list for yourself. What are some of the advantages and what are some of the disadvantages of the search? Pause now, and in a second I'll move on. The first advantage is that this takes many fewer comparisons than a linear search did. So just compare how many, in that example where you guess a number 1 through 100. If my number was 36, we found it in, I think it was 6 guesses, 5 or 6 guesses, 5 I think. But if you were to do the brute force algorithm, the linear search, it would take 36 guesses. 1, 2, is it 3, is it 4, is it 5, is it 6, and so on. So binary search got it in 5, that's much, much faster than 36. So it's a faster algorithm. A disadvantage, however, is that it requires the array to be sorted beforehand. So if you just had a random array of say, area codes, you wouldn't be able to use this. You need for these to be sorted because you need to know whether you can divide all the values up into an upper half and a lower half and be assured that all the values in that lower half are lower than all of the values in the upper half. So you need to make sure that your array is totally increasing. And that's a big assumption that you need to be able to make. We can compare the binary search algorithm to the linear search algorithm using big O notation, which we introduced last time. Again, in big O notation, n is the problem size, which can be different things for different algorithms. For our algorithms here, we're looking through things in an array, so the problem size is the size of the array. In the linear search algorithm last time, we said that the computation time is proportional to the size of your array. And that means that it's O of n, because the computational time is proportional to the size of the problem. That's what O of n means. So suppose that we have a particular problem and we have 100 items in our array and we run linear search and it takes 150 nanoseconds to run on average. If that's the case on this particular computer, how long do you suppose it will take to run 500 or to run the linear search if you have 500 items in your array instead of 100 on average? So go ahead, pause here, think about it, and we'll go through the answers in 5, 4, 3, 2, 1. So here's what I have. The time it takes to do 100, so t sub 100, is equal to k, some constant of proportionality, times 100 items, so n. So that means that k is 150 nanoseconds, so that's solving for t100 over 100, so 150 nanoseconds is t100 divided by problem size 100 gives us 1.5 nanoseconds per item, if you will, or something like that. That's the constant of proportionality for the big O notation here. So then on the other on the same computer, if we now have something that's 5 times as big, then we use that same constant of proportionality k, and that gives us, and now the 500 instead of 100, and that gives us 750 nanoseconds. So 5 times longer. Now you may have just been able to say, constant of proportionality, they're proportional, linearly proportional, so multiply the problem by 5, you should multiply the time by 5. And yeah, that's totally how it works. But it's a little bit more complicated when you have things other than just O of n. The constant of proportionality still plays a role. So let's see that for the binary search algorithm. On average, the processing time for the binary search algorithm is log n. Now notice it's log 2 of n. You may have seen log 10 of n or natural log, base e, Euler's number. Computer scientists like to use log base 2, because so many of the algorithms involve decisions where it's like higher or lower, or choose up, or just various decisions based on 2. And so it turns out that logarithm base 2 is perfect for that. So a lot of times you'll just hear people say, oh, it's just log n rather than log base 2n, or LGN is usually shorthand for log base 2, just like ln is shorthand for natural log. So log n. So the binary search algorithm is log n time. And so let's try an example here. Suppose that on another computer, or maybe the same computer, you have 100 items in your array, and let's suppose that the binary search algorithm takes 100 nanoseconds to run. How long do you suppose it will take then if you have 500 items in your array? Now to do this, use the O of n, or O of log n in this case. Think about the constant of proportionality, pause it, and see if you can come up with how long it should take to run. And I'll walk you through it in just a sec. But go ahead and pause it first. So here I am first going to express how long it is for 500 items. So time for 500 items is some constant of proportionality k, different k than before because it's a different algorithm, times log base 2 of 500. So I need to figure out what k is. So in order to do that, I'm going to look at the earlier value for 100 items and 100 nanoseconds. So there it was t100, or 100 nanoseconds, equals k times log of 100. So I invert that, and I can solve for k, and that gives me 15.0515 nanoseconds or so. Then I use that k back in the equation above to get t500, and that gives me about 135 nanoseconds. Cool. And that indeed is the final answer. So that's really, really cool. Notice that t of 500, or t of 100 is just 100 nanoseconds. Before with the linear search, if you multiply the array size by a factor of 5, then the time is multiplied by a factor of 5. But when you're running an O of log n time, then with this new algorithm, instead of multiplying the time by a factor of 5, it multiplies it by a factor of what, 1.35 or so? So this is much, much smaller. And you can check out the mathematics there too at the bottom line if you're interested. This plot compares the two algorithms for a bunch of different problem sizes. To get the data shown in this plot, I actually ran simulations. So what I did is I said, let's run this simulation, let's make an array of size, say, 300. So when I did that, I created the array counting numbers 1, 2, 3, 4, and so it had all numbers 1 through 300. Then I called linear search. I started a stopwatch, if you will, made note of the start time, and then ran linear search looking for random values for each of the different iterations. It was looking for a different value. Did that 1,000,000 times, and then I looked at the end time, calculated the difference in time for those 1,000,000 operations, then divided by 1,000,000 to see what the average number of nanoseconds per call was. And then I did the same thing for the binary search. And so I had a program that will do this for each of these two searches for a particular n. Then I ran that program 20 times here or something to get all these different dots here that you see. And what you'll see is that initially, for very small problem sizes, the linear search is actually a little bit faster than the binary search. And that's because the binary search algorithm has a little bit more overhead to keep track of. There's a little bit more branching, a little bit more decision making that the computer has to do. The linear search is very straightforward. Choose one, choose the next. Is it the first one? Is it the second one? Is it the third one? Because of that, the linear search algorithm is actually much faster than the binary search algorithm for very small values of n. However, at about n equals 50, it looks like here, the binary search algorithm starts outperforming the linear search algorithm. And so, if you look at the values from like the previous slide of n is 100, that's about 150 nanoseconds per time I call linear search for an array of size 100. If I multiply that by 500, the linear search algorithm we said before would be about 750. And in this plot, it turns out that it was about maybe 715, 720. So that was a pretty good estimate. Cool. Now let's see how the binary search worked. We said before that it would be about, if it took 100 nanoseconds to do a binary search for a problem of, an array of size 100, how long would it take for an array of size 500? We estimated that it would be about 135 nanoseconds. And here, if you look at it, it's probably about 140 nanoseconds. So our estimates were really, really close, which is kind of cool.